Hey everybody, let's continue the pendulum experiment. So from last time, you should have data that shows that the period as a function of the angle looks something like this, right? For different angles, you do a trend line, and you discover that trend line is about horizontal, meaning the period doesn't depend on the angle, and then also period as a function of mass. So for different masses, the trend line also indicates the period is not a function of the mass. And that aligns with our hypothesis that we expected the period to behave like this. So not a function of mass, not a function of angle, but it is a function of the length. Although not in a linear fashion. See how there's a square root? So we're thinking that the data for different lengths, the period's going to look something like this. Okay, so we need to show this trend. If you don't take enough data, right, it might look like this. Like it might look like it's a linear relationship. So then you need to collect enough data that you see this pattern emerge. So for practical purposes, right, try and get as big of a range as possible. So let's say like as short as, let's say 10 centimeters and as long as at least a meter. So I happened to set mine up at the top of a door. So I had the entire height of a door to work with for the length of the pendulum. So it just depends on how you set it up, how much room you have is like how long you can make your pendulum. And then just practically, when the string is short, it's going to swing back and forth really fast. So it might be hard to time. If you video record it and count frames, that's no problem. But if you're using a stopwatch by hand, your reaction time is going to factor into the period more when the string is really short. So there's a practical range that depends on your particular setup. Okay, so let's say try to aim, let's say 10 centimeters to at least 1 meter. And then you want to have enough data points. So let's say at least 10 data points. At least. And then because you're taking so much data, how about we go 3 trials per length? Right, when we did mass and angle, we did 5 trials each, but since you need a lot more data, even 10, like you may need more, like 15 to 20 data points to see this pattern, at least 10. So for example, let's see. So let's say you have length, I'll make a table. And then you have your trials. And then, right, so for example, if you start at 10 centimeters, and then you, let's say you let it, if you time it by hand, you let it swing 3 times, stop the stopwatch, divide by 3, and then that's 1 trial. Reset, and then again, let me jot this down. This is for small angles. So let's make a restriction here. Let's keep it to less than 10 degrees. Oh, less than or equal to 10 degrees. And then you only want to adjust one variable at a time, right? So make sure you use the same angle for all of these trials and the same mass. Same angle, same mass. So you're only changing the length of the string. Okay, so for example, let's say we go 8 degrees and 10 grams for all of these trials. But then we're adjusting the length. Okay, so then you saw 8 degrees, 10 grams, 10 centimeter length, let it go, goes 3 times, divide by 3, there's trial 1. Reset, let it go, swings 3 times, divide by 3, there's trial 2, reset, swings 3 times, stopwatch, divide by 3, there's trial 3, then take the mean of these, and then that goes right here. Right, and then you just do for all the different lengths up to at least 1 meter. Trial 1, trial 2, trial 3, there's the mean. And then these values are what make this graph. Okay, so then let me just show some footage of some of the data I took. So this is, I let each of these lengths swing 3 periods, and then I did 20 different lengths. Okay, so let me start it off. Ready, go. And see how when the string is short, the period's like really short. So it might be hard to time it by hand. Your reaction time is going to factor into that. And then as the string gets longer, you might notice qualitatively observing the period is getting longer, right? So longer string takes a longer period of time. Okay, so then a longer string, a longer period, and just depending on where you have your setup will determine how long the string can go. So you see I have this entire height of the door to work with. Okay, and then it's not obvious when we observe qualitatively whether this relationship between the length of the string and the period is linear. We don't know, right? So that's why it's up to you to collect the data and determine quantitatively what's happening here. Okay. So I'm not sure how helpful this is, but I have 4 different lengths set up here at the same time on the screen. And then we expect the period to be different for each this time, right? And the longer string should have the longer period. And then I'm running this at half speed. So ready, start. And as expected, yeah, the period is different. Unlike when we did this slow motion video for the angle and for the mass. But still, we don't know if it's a linear relationship between length and period. Okay. So, again, it's up to you to determine quantitatively what's happening. And we're hypothesizing it'll look like this. So you need this graph. Now, the last thing we wanted to do was to measure G. So how do we do that? So this is non-linear. So let's linearize it. This equation is non-linear. How do you linearize it? How do you get rid of this square root? You just square it. Right? So you have t is 2 pi root L over G. Just square it. Right? So then t squared 4 pi squared L over G. There you go. Okay, now let me rearrange this a little bit. I'm going to move the G right here. Okay. And then just put this in parentheses like this. Okay, so take a look at this. What if we graph, instead of period and length, period squared and length? So period squared. It's going to look something like this, because now, look, it's linear. Period squared is a linear function of L. Okay, so how do you graph this? If you look at your data, right, you have length here, and then this is period right here, right? This is the mean for period. So you just make another column, period squared. So take this number and square it. Whatever the number is here, square it and put it here. Whatever this number is here, square it, put it here. And then you graph t squared and length. T squared versus length. And then you get a graph that looks like this. And then make sure t squared is on the vertical axis and length is on the horizontal axis. And then you can do a linear fit, because now it's linear. And now look at this equation for the trend line compared to this equation. What is the slope? This is the slope, right? This. These are the same. So when you do your fit, your trend line, whatever the slope is here, get that number, right? Because that slope from your fit, m, is this, 4 pi squared over g. So let's rearrange, let's trade these. That means g is 4 pi squared over m, which is the slope you got from your trend line. This one, right here. Right, so look at this. This is the slope you got from your trend line. You do this 4 pi squared over that, and you'll get a measured value for g. And then you can compare it to 9.81 meters per second squared, which you're expecting. And I think it'll be pretty close. So then just put this in your report, what you measured, what you computed for g. Okay, so there's a lot to do this week. So, right, because you have a lot of data to collect. And then you make this graph here, period versus length, and it's going to be nonlinear. And then square it, so you go period squared versus length. And then you need this trend line, the slope of the trend line, so that you can calculate g. Okay, so lots to do. Let me know if you have questions, just put in the forum, and I'll see you on the next video.